Okay, so we're recording now, and I'm going to go back to the share. All right, so here we are, a non-linearly separable set, but we are going to linearly separate it. So how are we going to do that? So you can't express this equation for the unit circle and as in terms of the variables x1 and x2 without squaring them. So you can change the variables so that instead of working with just the naked numbers, you decide to work with their square instead. So this is a transformation. The book calls this the X space for the, this is a row of capital X. You have to turn it sideways to actually make it a row, but that's what the rows of X are. These data points turn sideways. And if you square its entries, you get what the book calls little z. And now this turns the matrix big X into a different matrix big Z. So in terms of the numpy, what's happening here is we're squaring this column and squaring that column. And you can actually see down here that's like literally what happens on this line. So PTS2 is just the points. So the X and Y coordinates of the points. This matrix is like 2 columns and like 100 rows or however many points there are. So when you do this in NumPy, it just squares each element respectively. And so this is what does the transformation that's described there. Now in this new coordinate system, if you want to express the decision boundary, this is just the equation for the decision boundary. It's the same as the unit circle, but I moved the 1 over to the left here. Now that can be expressed as a dot product with W. So it turns out that in a linear model, what really needs to be linear is you just need to take the dot product of a vector W and some vector of X's. The vector of X's can actually include sort of non-linear functions of the original variables. The thing that makes it linear is that it's kind of linear in W, not in X. So all these linear techniques, they work fine if you change the X around. It's just that you still, the hypothesis is still going to be based around a dot product with a W vector, a weight vector. And so if you take this W and take the dot product with this X, then you get exactly this expression. And so, the sign is going to be positive on this. So what is this going to be? This equation is going to describe the unit circle. The sign is going to be positive on one side of this boundary and negative on the other. And so after this transformation, we can express the separation as a linear function. And this is the Z space. So now we're looking at the same data points, but with their coordinates transformed according to this transformation. And it looks like this. And if you zoom in, you can just see that now it is linearly separable. You just separate it with the line that goes like that. And this is the weight vector that corresponds to that linear separation. Okay. So in that case, we just transformed the variables that we already had. But usually what you do is you add new variables. So let me give an example of that. So here's another data set. It's not exactly linearly separable, but it's close. So the way I made this is I just made a bunch of points, and then I colored them blue on one side of a line and orange on the other side. Here's the line, that's the actual separator. But then once I had them separated, I randomly flipped 5%. So here, it took me a while actually to figure out how to do that. Here's the line that does that. This is XOR. And so G is truth values, so I'm XORing with some other truth values, and it's 95% false, which will do nothing under XOR, and 5% true, which will flip the status. So that flips 5% of these points, and so you end up with something that's not linearly separable exactly. And here's the boundary that's created by the line that really sort of is separating the data here. And the error is about 7.5%. That's a little bit unlucky because the the way the probability works, I should be wrong only 5% of the time. It's just that the probability distribution, I used a probability distribution, and so I got, there's a little bit of variance. So it's not necessarily exactly 5% because there's a small chance that none of them get flipped and a small chance that all of them get flipped, and so forth. So it turns out that a certain number of them got flipped. How many? 1, 2, 3, and I guess 3 flips gives you 8% error or 7.5% error. So that's what happened. So now let's beef up the matrix X. So the matrix X initially has 3 columns: a bias column, the column for the first variable, and the column for the second variable. We're going to retain all of those, but then we're going to add a bunch of nonlinear functions of those as well. So we're going to tack on an extra column for the first column squared and the second column squared, and the respective products of every entry in the first column and the second column. Then we're going to add the first column cubed, the second column cubed, the first column to the 4th power, the second column to the 4th power, and the product of the squares of the first column and the second column. So there are 2 ways to understand what's happening here, and they're both cool. One way to understand what we just did is we sort of embedded these, ignore the bias column. These are really points in 2 dimensions, and we just embedded them in 10 dimensions. So it's sort of like sending the plane into a higher dimensional space, and that is impossible to visualize really, but you can think about mapping the plane into 3-dimensional space, right? We do that all the time. So imagine that it kind of got embedded in a higher dimensional space, and it's kind of wrinkly. So if you take like a wrinkly blanket and you cut it with a plane, like a hyperplane, you can cut out kind of weird regions that you wouldn't have been able to cut out before if it weren't wrinkled. Like a simple example would be take a cloth and then bow it out like an umbrella, and then take a samurai sword and chop off the top. Then you've just cut a circle out of 2-dimensional space by using what in 3 dimensions is a plane. I hope that makes sense. The other way to understand what's happening here is that this will end up really just being a polynomial function of with 2 variables and coefficients that are determined by W. And so you could plot this thing in 3 space, and then what ends up being above the XY plane is going to have one kind of classification, and the stuff that's below the XY plane will have another kind of classification. Okay, so here's how you actually do this transmogrification in Python. I'll show you a slicker way to do it, but this, if you want to just do it blood and guts with NumPy, not using sklearn, this is how you do it. And if you check things out here, so here's the first column, here's the second column. This is just doing all those transformations. So now I have literally the Z matrix now. So we're in the Z space. So we just do gradient descent, and we could have used the normal equations too. Okay, sorry. We're using logistic regression. So we have to use gradient descent because this is a classification problem, duh. And we end up getting this weight vector. And so here's the soft boundary that results from that. And you can see that it's curved. So because it's no longer, what you do is you put the 2-dimensional sheet up into higher dimensional space, cut it with a samurai sword, and that cuts out all kinds of weird holes. And then you pull it back down into 2 dimensions, and what you see are these weird holes that were cut out by a plane in a high dimensional space. But this is logistic regression. So logistic regression, assigns a probability to every point. What is that probability? It's the probability that y is 1 given the point. So that's what this shading is corresponding to here. So the color of each point in the plane is the probability that the classification is 1 for that point. And this color bar over here tells you how it works. So it's very certain. It's giving you a probability estimate of like 1 over here. What it's saying is that I'm very sure that any point over here is blue, and the opposite is true over here. It thinks that in this purple region, it says that the probability that these things are blue is 0. And so the alternative to being blue is being red. So it's certain that they're red over here. And then in between, there's kind of a region of uncertainty where it's green, just because the way the colors work here. You know, green is what's in between yellow and blue. So you can threshold that. And let's see if we can find the line where it actually does the threshold right there. So yeah, okay, so these z's have not had the sigmoid function applied to them yet. They have not had the logistic function applied to them yet. So you can just take this sign. So if you take the sign of the dot product of w and x, then you get 0 or 1. And you know, if it's a sorry, you get -1 or +1. And that just exactly corresponds to when the sigmoid will make it above 0.5 and when the sigmoid will make it below 0.5. So it's the same operation. Anyway, here's the decision boundary that you get. And what is the error here? Oh my gosh, the error went down. So naively you think, great. But you might also be a little bit worried, because in this example, we know exactly how this problem works because we created it. We know that there's really this linear separation, and it really is a linear separation. It's just a little bit noisy. So there's kind of like 5% noise here. And you wonder, if we start adding more points according to this same sort of algorithm for generating the data, what's going to happen to the accuracy of this curve? So those of you who watched the videos, anybody want to say?
Can I guess?
Mm-hmm.
I assume it'd get better.
So if you could think of what we have right now as being like the training data. And then what we're going to do is we're going to go out into the real world. And so data points are going to start coming at us that we've never seen before, maybe a data point there, a data point there. And what we really care about is how we're going to perform on these new things that we haven't seen before. So in this region over here, we're going to be wrong always, because, well, we'll be wrong 95% of the time over here, because, you know, from this picture here, you can see that those things will really be blue with 95% probability. So in this purple region over here, it's going to be wrong 95% of the time. But it actually does okay. That's sort of like its only flaw, really, aside from these little jogs and jags here. So let's do it. Let's, I'm not sure what that is. We're supposed to add a lot more points. Okay, so here we go. So now this is sort of a simulation of that. So we're looking at the out of sample error of this decision boundary. The reason there's this white stuff over here is because there are some points that landed in regions that the training data never landed in. Sorry, that's kind of ugly. And we can look at the error that it has now. So this is closer to the out of sample error, because these new points are just sort of coming along after we've already decided on our boundary. And now the error is at 8%, or 8.25%. And okay, so how does that compare with just the original line? The original line, we know that asymptotically the error of the original line is 5%, just because that's how the data gets made. Right now it's 3%. So the the simpler model is actually doing better here. So simpler, one way to, there are many ways to understand simple. If you really want to understand what it means to talk about the complexity of the hypothesis space, you have to go through chapter 2, which you should do at some point in your life probably, but it's kind of complicated. But a simple way to understand what complexity means is number of columns. So this, in this learning algorithm, we just had an X with 2 columns and 1 bias column. And this X, we had an X with 10 columns and 1 bias column. So that is sort of more complicated. There are more possible curves here. And the more complicated hypothesis space did better than the simple one on the training set. It had a lower error on the training set, but then when we left the training set behind and went out into the real world, it did worse. And this is kind of like we talked in the beginning of class about sort of getting lucky and how performance is the result of 2 things, luck and skill. And skill persists and luck doesn't. So when there are a whole lot of decision boundaries, a whole lot of hypotheses in the hypothesis class, when you fix a data set like this data set is going to be just like the greatest data set ever for some lucky hypothesis. It's like, oh my God, it's my birthday. This is the data set. This is the training data set that I was born to divide. So they get really lucky with respect to the particular training set, but then that was really just a function of that particular training data. And if they'd gotten, if we'd seen other training data, then somebody else would have gotten lucky. And so they're not really capturing just like the statistical nature of where data comes from. It's more like they're getting extremely lucky with respect to the particular training data that we happen to get. So their performance is exaggerated because, you know, in the luck plus skill equation, they have lots of luck. And all this is kind of just a fancy way of saying that complicated models tend to overfit the training data. And the training data gives really optimistic estimates of the performance of the classifier. And we're gonna be talking about this topic for quite a while. There's like a lot more to say about it. So right now it's 11:30, and it's time to go on to something else. But how's everybody doing? Any questions about that?
I have a question, Professor.
Sure.
Sorry, the transformation you did on the top, is that the only transformation, or I mean there are other ways to do that too? Are there
Yeah,
other
there's
transformations
like
too, or that one only?
this one, the one with the unit
The
circle.
one you took.
Oh,
Yeah. X
this one.
squared.
Yeah. So this one is just like a proof of principle, and it's a really simple example.
Okay.
And it's just to show that with a certain transformation of variables, you can use a linear model to cut out a circle. And so it's not the only one.
But are there any other? Are there
Yeah.
any other transformations besides?
Yeah, anything you
Okay.
can think of. You can add like quotients. You know, like in medicine, one way to tell if a person is sick is if they like maybe it's not exactly the level of hormone A and hormone B. It's like the ratio of A to B. So if you have a column for like thyroid stimulating hormone and like another column for estrogen, maybe the thing that really determines whether the person is sick is like the ratio of those. So you could add a new column for that. So you have a lot of freedom.
I get it.
Yeah, you have freedom to design the transformation, but you pay a price when you add columns, and that price is that your model starts to overfit the training data. So it's kind of a trade-off. Any other questions?
Okay.
Okay. So what we just did is like transformations of variables and classification. We did kind of an introduction to that. And of course, you can do the same thing with regression. So you should have some slides here. I think everybody got these, right? Let's just.
I don't seem to have them. But...
Oh, okay, sorry. So let's see. So I have under handouts here. Oh, yeah, sorry. It does this sometimes. It got stuck at 7 out of 19. So I'm going to click that and hopefully that will solve that problem. So what I'm looking at here is in slides, there should be a directory called ZSpace. So only 7 people had it. I'm sorry about that. But everybody else is getting it now. And the one that we are going to look at next is polynomial regression. So this is kind of similar to what we did before. Maybe I better go over to the sheet and just do some math. Okay. All right. So let's say that we have one variable x1. We can look at all the polynomials that we can make with polynomials. And then so let's just consider degree 1 first of all. So degree, you know, I think a better way to do this would just be to say that here's a column for degree, and we'll consider different degrees. So first, let's consider degree 1, and the variable is just x1. So you can do sort of a plus b times x1. Okay, so in terms of a matrix X, what this is just sort of like you have a bias column, and then you have a column for x1. Okay, so now what about degree 2? Then you can do polynomials like a plus bx1 plus cx1 squared. And now in terms of the matrix X, it's like you have a column for the bias, and you have a column for x1, and you have a column for x1 squared. And then these coefficients will just be W. So W will take care of those coefficients. And you keep going like that. So I think everybody's familiar with this. Everybody knows what degree 3 is going to look like and so on. But I think you probably have not seen many multivariate polynomials. So now consider the same game, but now there are 2 variables, x1 and x2. And let's make a column for the degree. I think I'm going to regret putting it there. I'll put it over here. Are you guys with me? Are you looking at me scribbling right now?
I get it. Well,
Okay.
but I'm watching.
Okay.
Yeah, I'm listening. I'm watching.
Yeah, but you can actually see that I'm writing on this piece of paper?
Yeah.
Okay.
It's in red writing.
Okay, good. Okay, so degree 1 polynomials with these 2 variables, you just have, you know, things like a plus x, plus bx1 plus cx2. Okay, so those are the degree 1 polynomials. And so the data matrix X has just a column for 1 and a column for x1 and a column for x2. And then W takes care of the coefficients. Now here's what's going to be a little bit surprising maybe. Degree 2, what does a degree 2 polynomial look like in 2 variables? So you have a constant term, and then you have the linear part. So you have exactly what you had before, but now you have extra stuff too. You have d times x1, x2 plus e times x1 squared plus f times x2 squared. So now it kind of is a little bit more combinatorially explosive. So how many columns do we have now? We have a column for 1. We have a column for x1. We have a column for x2. And we have a column for x1, x2. We have a column for x1 squared and a column for x2 squared. Okay,
How
so
do,
that, yeah, sorry.
how does 1 more degree add that many variables?
Yeah, so look at each term here. So each term has some number of x1s and x2s. So you can do the combinatorics here. So what have you got? It's like this chooses this is 0 x1s and 0 x2s. This is 1 x1 and 0 x2s. And I'll just write the numbers instead of, right? So this one is 0, 0. This one is 1, 0. This one is 0, 1. This one is 1, 1. This one is 2, 0. And this last one is 0, 2. So it's kind of like, I can't come up with a formula off the top of my head, but can you help me kind of characterize what's happening here? So you want to pick two numbers in the range 0, 1, 2. Okay. Oh crap, that's not right. So I don't think I should try to do this off the top of my head. Let me get back to you with the formula, and maybe I'll even make a little video deriving the formula. But the point is that, like Kevin was saying, it is, I think that was Kevin. It's surprising that this number grows so fast. And then this is just with 2 variables. If there were 3 variables, x1, x2, x3, and you go to degree 2, then there's going to be all kinds of crazy stuff. You're going to have a column for the bias for each one individually. And then for all products of 2 of them, x2, x3. And then for the product of all 3 of them, x1, x2, x3. But that's not all. Oh, no, that's not all. You also have x1 squared times x2, and you also have x1 squared times x3. And then you have x2 squared times x1, and then you have x2 squared times x3. And then you have x1 cubed, x2 cubed, and x3 cubed. So these are how many columns, right? The columns just exploded. I started out with a data set that had 3 columns plus a bias column. And now I have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 columns. So just be aware of it. The number of columns increases really fast, and that's why, even though your professor is too dumb to know or to be able to exactly quantify how many columns there will be as a function of the number of original columns and the degree of the polynomial, it's big. Okay, so I think that makes the point about that. So let's come back to this and polynomial regression. So now we're going to do regression on this data set. And so we've been doing linear regression. So we can do linear regression and just come up with a line that fits that data. So there's the best fit line. So this is like degree 1. And this kind of explains why here. So I started out with data that just has 1 column because, this is like, how does regression work? The x-axis is like x1 and the y-axis is like y. So in regression, y's are the real numbers. So what we're plotting here is like x, y, literally, same notation. Okay, so when we do a degree 1 transformation, that just adds a bias column. And here's how you can do it using the sklearn library. This is much simpler than writing your own code to do this, which is what I did the last time I taught this class, but I didn't know about this. So how do you do it? You import polynomial features. You tell it what the degree is going to be, in this case 1, and then you do you know, you might have noticed in the scaling functions you can fit, and then you can do a transformation. If you want to do both at the same time, it's fit transform. So this fits the matrix and then also makes the transformation. And so here's what it looks like afterwards. And degree 1 transformation just adds a bias column. It's actually a nice way to add a bias column. Okay, and so then the best fit just turns out to be a line. Okay, so now let's do degree 2. So we start with just one variable, and now when we go to degree 2, you have 3 columns. So it looks like this. Here's how you do the numpy. So now you are fitting it with a quadratic. And the way I made the data is actually quadratic. So there's some noise also, but it's basically quadratic target function. So the performance here is pretty good. This is the R2 score is 0.88. For the linear, for the line, it was 0.77. So the R2 score has gone up quite a bit. Now let's look at a degree 5 transformation. So that looks like this. But notice that it's starting to get kind of crazy, and the R2 score here is 0.92, so it's even better than before. So the R2 score is going up. But do you think this kind of captures the nature of the data as well as the quadratic curve did? Sort of like this squiggle is more like just a weird feature of this particular training data, and it doesn't really have to do anything with the distribution that generates the data that we're interested in. So okay, but still it's pretty good. Now let's go up to degree 30. And there's this weird picture. You notice that the scale kind of explodes here, so the data looks flat because the polynomial that you get is so curvy. But if you fix the viewing window, it looks like this. It's kind of interesting, isn't it? So now the degree 30 polynomial is getting a really great score. It's gone up to 0.96 R2 score, and it's just kind of trying to go through every point. But is this going to generalize well? You know, if new points start coming along, let's say that we get like, we actually, now that we've built this model using the training data, we try to use it, and we get a new example from nature, and it happens to be like in this region right here. Then the prediction from the model is going to be insane, right? It's going to be incredibly wrong. And the same thing in some of these other places. You can see like the.
So I have a question.
Yeah.
So it seems like, okay, if we were to continually increase the amount of degrees, no matter the data set, wouldn't it just try to keep finding at any point within the space where it could fill it? Because it kind of just seems to be filling up more and more of the space in general, meaning by chance it's going to get more of the points. It's just as long as we increase the amount of degrees.
That's a good question. Who's asking that question?
Reagan?
Reagan, I thought it might be you. Okay, good question. So it turns out that I forgot how many data points there are here. Let's go back and see how many data points there are. How many points were there? There are only 20 points. I think, anyway, I think there's 20 points there. That's not right though. There's more points than 20. Where did this data come from? Number samples equals n samples. Is there really only 20 of them? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There are 20 of them. Okay, so you know that 2 points determine a line, right? and 3 points determine a parabola. And then, you know, parabola is degree 2. It takes 4 points to determine a degree 4, all the coefficients of a degree 4 polynomial, and so on and so forth. So with 20 points, what I'm saying here is going to be a little bit contradictory. So with 20 points, there is a degree 20 polynomial that goes through every single one of those points.
Yeah, that
And
makes perfect sense.
yeah, and so that would actually have an Insample error of 0. And why, you know, and then for higher degrees, it'll still just keep finding a polynomial that goes exactly through those points, and it might actually still be the same polynomial. But you can see that this, even though we were up to degree 30, it misses a couple points here. And so why is it not getting those? It could just be that the algorithm, the training algorithm, no, it should find them, right? Because the normal equations with linear regression should find that. But what happens when you do when you solve for W? We use the pseudo inverse. That's how we're doing it now, I think, right? Where are we actually getting these W's? Oh, right here, right here. Okay, see how I'm doing it? Right there. All right. So that has to do what? That has to compute the pseudo inverse. So that pseudo inverse involves 3 matrix multiplications and 1 matrix inversion. And also the matrix that's happening to is pretty big. It's 20 by 30. So when those operations happen, there's some floating point error inside the machine. It some of those multiplications exceed like the you know, the ability of a floating point number to represent them. So that causes some error, and you can actually see that here, and that's why these points are being missed, even though a 30-degree polynomial should be able to fit 20 points exactly. It's kind of a long-winded answer, but yeah. So 30-degree polynomial should theoretically be able to fit 20 points exactly. And if you really care about finding a better fit, there are instead of just using these polynomials, there's a smart way to do it, and they do it in the book, but I forget exactly the reference. But you can use sort of a basis for polynomials. Those of you who have taken linear algebra will understand this point, and nobody else will. So what is a basis for the space of degree 30 polynomials? So the most obvious basis is just x squared, x cubed, x to the 4th, etc. But it turns out that there is a basis for degree 30 polynomials that has better properties. It's like an orthonormal basis. And so then each basis element is itself like a high degree polynomial. And that if you use those instead, you get better numerical behavior and you don't get things like this. Okay, sorry. Okay, so now we're gonna consider the out of sample error. Let me just check on the time. Oh, we've got time. So we're gonna do this with a lot more points that are drawn from the same distribution. So this will be like the real test of how these models behave, because we're looking at a lot of new data. So this, when we look at how they perform on this bigger data set, it'll give us an estimate of the out of sample error. In real life, we don't get to do that, but in these examples that we make up, we can. So here's the degree 30 fit, and look, it's terrible. The R2 score turned negative. Anybody want to say what it means when the R2 score turns negative? What does that mean?
Isn't the R2 score like a measure of error? So if it's negative, isn't it good?
Oh, that's interesting. Think of R2. R2 is the percent of variance in the data that's explained by the model. The highest it can be is 1. So if R2 is 1, that means all the variance in the data is explained by the model. And that's like the best possible model. At the other extreme, there is an R2 score of 0. And the thing that achieves the R2 score of 0 is just taking the average of y and letting that be the model. So if I just took all of these points and projected them onto the y-axis here and took their average, and then let the model just be the line that went through there, the horizontal line, that's like the constant solution, just the constant y bar, you know, it just, you give it any data point and it just predicts the average of the y values that it's seen. So that prediction has nothing to do with x. It only has to do with y. So it's getting 0 information from the x's. And so what 0 R2 score means is you're doing as well as you can do without looking at x at all. But this is a negative score, so it does even worse than that. So this model is even worse than the model that just constantly says y bar. So it's doing even worse than you could do without looking at x at all. So it's not good. That's not good. Okay. It could be actually a lot more negative. It's not that negative. So I don't know, but you can see that it's bad, right? Okay. All right. So it doesn't work well out of sample. And degree 5, how does that work out of sample? Actually, pretty well. But still, the performance went way down. The performance went from like 0.9 down to 0.78. And here's the quadratic fit. And I think the in-sample error was like 0.88, and now the out-of-sample error is 0.84. So those are pretty similar. Also notice that that R score is the best. So, you know, R2 score being close to 1 is good. So this one is the best one. All right. So these others were able to get really low training error, but because they were so complicated, they were able to sort of memorize the training error, and they didn't really get the broader picture of how the data was behaving. So actually, by having some constraints on how complex a hypothesis could be, we sort of force it to think more about like the general probability distribution of the data, and it makes it perform better out of sample. And here's the line. So the line is 0.665, and that's probably very similar to its in-sample error too. I forgot what that was. What was the in-sample error for the line? Just gonna make you guys have a seizure or something. Oh, it's 0.77. Okay, so even for the line, it went down quite a bit. Okay. All right. So here's kind of a little bit of a wordy bit. All right. So we can go back to this theoretical stuff that we were talking about really early in the semester about, you know, when En is a good approximation for E out, and you know, in practice, you never actually get to see E out. We split the training data into testing and training parts, and then we can use the testing part to sort of approximate E out, and that's sort of the best idea we ever get of it. But usually it's just out there and we don't know it. So we want it to be the case that En is close to E out, and we also want E out to be as small as possible. So that's the thing that does these two things the best is the quadratic model. Now we're going to start talking about bias and variance, and bias and variance is probably all that we're going to talk about on Thursday. And so let's look at these two sentences here. So simple models are biased. Biased is a very overloaded word in machine learning. So it has at least 3 different meanings. But usually what you should think when somebody says that here's a machine learning model that has high bias, what that means is that the model is too simple for the target function. Like in this example, the model with the highest bias here is the linear model, because it's not simple enough to capture this curve in the data. So that's what bias is the hypothesis set is contains hypotheses that can't really capture the richness of the target function. Okay, so that's bias. And now what is variance? Oops, sorry, I lost my place. Extremely complex models have a problem called variance, and it's kind of hard to understand what variance is. We're going to do that in the next slides. One way to understand what it means is that the out-of-sample error is extremely dependent on which particular training set you get. And so I actually made some pictures here that kind of show those things. So the model with the highest variance is the degree 30 model. So this is high variance, but low bias. So it has high variance because the output G is very dependent on the training data. But it has low bias because it is rich enough to actually exactly capture the curve in the data. And the degree 5 is actually a pretty good trade-off between the two. It has very low bias because it can represent a curve, but it has a little bit of high variance because this little hump and this twist and stuff, those were just features of the particular training data that we happen to get. So it's a little bit sensitive to which training set you get that makes the variance high. And then the ideal balance between the two in this example is the parabola here. So it has low bias because it can represent the curve perfectly, but it also has low variance because it doesn't depend crazily on exactly which training data you see. Okay, so in a certain technical way, which we'll explore next time, the expected out-of-sample error of in regression, when you're using the mean squares error, the expected out-of-sample error is bias plus variance. That's assuming that there's no noise. But we'll talk about this a lot more next time. But where does error come from in regression? You can do this derivation where you prove it comes from 3 places. 1, noise. 2, bias. 3, variance. So those are like the 3 things that that make a model bad or good. So also there's a trade-off between the two. When you make variance high, you make bias low, and when you make bias when you make variance low, you make bias high. So this one is high bias, low variance. This one is high variance, low bias. And this is the ideal trade-off between the two here.
But it's all dependent on the data set.
Yeah, that's right. So, you know, we can say that variance is what happens when your hypothesis set is too complicated. But right, too complicated for what? So if, you know, here the sort of the complexity of the data is degree 2. So then degree 30 is too complicated. But if it were degree 30, then a degree 30 model would be just right. So that's an extremely good point. So you get high variance when the hypothesis set is too complicated for the data that you have. Okay, and then here's some learning curves. I guess we'll finish with these. So what are we looking at here? Here I'm training it and testing it on just a fraction of the data. So we have, is this with a real data set? What data set are we using here? Okay, so this is the training set size. I must have upped the size of the training, or maybe this is 500 points actually. I think that's probably 500 points right there. So the size of the training set is going up from, oh, you know what? I think it's 1,000 actually. And I keep 500 set aside for testing, and then we could use up to 500 for training. That's what's happening. So look what's happening here. This is the degree 1 model. So this is the line, and it shows what happens as the training set size increases. So the training error goes up and up because with 2 points, a line has 0 error. Then with 3 points, the error is a little bit more, and so on, up to a certain limit, and that limit is just how well a line can do on data that has that distribution. So as the size of the training set goes up, the the testing error comes down, because the bigger the training set is, the more representative it is of just the way the data is, and so when the training data represents the way the data really is, then the line that you produce works better for just the nature of that data, and that makes the test error come down. So notice that they slam together pretty quickly, and the sort of asymptotic error rate here is about, let's just call it 0.4, okay? And so this is a high bias learning curve, because the average best hypothesis is not that great, and it quickly converges to a high error rate. So now look what happens with degree 2. Look, it converges to something that is much lower, right? Converges to a lower error rate, but it still converges fairly quickly. Not quite as quickly as before, but the training and test error come together here at about like 50 maybe. Okay, so this is kind of perfect. And now with degree 5, you can see that it's starting to, for one thing, it takes longer for these numbers to come to, for these tracks to come together. And, but they do come together to a low error rate. But you see some thrashing happening here. Anybody want to explain why it's starting to thrash a little bit here for the low training set size?
That's the variance, right?
Yeah, so variance is sensitive dependence on exactly which training set you get. So for some training sets, you're getting a curve that gives you very high test error, and other times you're getting a model that gives you very low test error. So the best is low, so it's converging to like a low error rate, but because you have more degrees of freedom in the model, it takes more training data to sort of to constrain all 5 of those parameters and give something that sort of reflects the way the data really is. And now it gets completely crazy with, oh, so I put in one of degree 10 here. So I would say that these things have not really sort of, the test error is not settled down here. So what's happening is we don't really have enough data to have a degree 10 model here, because 500 data points is not enough to kind of constrain the degree 10 enough that the training set kind of looks like the test set. And this is high variance because you can see that the which model comes out is really dependent on which training set you get. That's what makes it look kind of, it's because it's highly dependent on exactly which training set you get. So you're getting a different training set each increment here, and then the performance like wildly depends on which particular training set you get. And here that's like, very much the case. So now its behavior is all over the place. If we had more data, this would eventually settle down and be calm, just like everything else. We just don't have enough data for the degree 30 model. But if we had, 8,000 data points, that would be enough probably for the degree 30. Then we would see it settling down just like everything else. So degree 30 is a more complicated model than we can afford with the data that we have. And that's the end of these slides, and that seems like a pretty good place to stop. I put an activity in the activity folder, which you can look at, but we didn't have time to get to it. I don't know if we ever will have time to get to the activities, but if you want to, you can play around with that. Okay, any last questions? There's Tyler with his baby. You're not actually holding the baby right now. That's your profile picture, right? Oh, I should take attendance. Let me take attendance. Whoops. So we now have 21 people, which is more than is even in the class, so that's great. And Usama?
Here.
Got you. Reagan is here. Agnes is here. Velko? Is Velko here? Is he? I don't see him on the list. Velko. If you know Velko, I worry, since he's not here and he's a good student, I wonder if he's getting the Piazza messages. So if you know him, maybe you could send him an email and ask him if he's on Piazza with us. Jenk?
Here.
Got you. Al Haji is here. And Yuri is here. Hope you feel better soon. Kevin is here. Andres?
Here.
Got you. Jose is here. Hi, Jose. And Levon?
Here.
Levon is here. Julio?
Here.
Julio is here. Romerson?
Here.
Got you. Tamer? Tamer is here. Young men?
Some people don't have
Microphones.
mics.
Sorry.
Yeah.
Okay, great. I'm glad. Okay, so I see that he is there. And so Velko really is not here, right? It says,
No, Velko was here, but I think he might have left because he said something in the chat.
Oh, yeah. Okay, I've got him here.
I'm not sure, maybe if he doesn't hear us or...
Yeah. I think maybe he got bored and left. And okay, so Raymond?
Here.
Raymond's here, and Chong is here, and Tyler is here. Iqbal? Is Iqbal here? Anybody able to see him in the list? I don't see him. Okay, and that's everybody. So have a great Wednesday.
I have a question, Professor.
Sure.
I need some extension on the homework 3, actually.
Yeah.
I was working, the tutoring thing for one of your class and the schedules, everything. I was gathering all the equipments last week, couldn't get time.
Okay.
I did half of it, but I need some more time.
Okay, everybody can have until Thursday. Then maybe, in class on Thursday though, let's go over the answer. Okay, so everybody can have until the beginning of class on Thursday.
All right, thank you.
Okay, bye.
Professor, when would be a good time to schedule like a one-on-one? Just basically to maybe go over the homework or maybe give some tips how I could code that code?
Like maybe 10 a.m. tomorrow.
10 a.m. tomorrow.
I'll open up this, I'll open up this same Zoom thing here at 10 a.m. tomorrow, and anybody who wants to come can come.
Okay, that'd be great.
All right, okay, same place.
Thanks so much for your help, appreciate it.
You're welcome. Okay, bye everybody.
Hello.
Bye.
Okay.
Anybody have a question? Okay, bye.